Hi, this is Jason McIntosh. In this video, I'm going to take you through the Ares Nonlinear Acoustic Modeler. The modeler is a part of the Ares Acoustic System. Once you get the Ares software, you create a nonlinear model instance inside of Ares by selecting the new modules menu and then selecting Nonlinear Modeler. Hopefully you're already familiar with the linear modeler in Ares. This has some similarities, but it's quite a bit different. One major thing about this modeler is that it deals with fixed topologies. You can't change the way these elements are connected to each other. That's fixed in the model. As you click on the elements, the parameters for those elements appear below the model. The system parameters are in the voltage element. This is a bit different than the linear modeler. When you click on the voltage element, not only do you get the voltage that will be used to drive the circuit, but you get the starting and ending frequency for the analysis, the number of frequency points, the iteration range, and also there is this ability to choose different solvers. These are discussed in detail in the manual, but for now I'm going to keep it simple and I'm going to stick with the nonlinear lump parameter model, the solver, nonlinear solver. This is going to be the fastest of the two nonlinear solvers listed. There's also the graph element, which we're already familiar with from the linear modeler. You can plot a variety of quantities from the model and copy the current solution into these graph buffers for later plotting. We'll be demonstrating this a little bit later on. There's also an options dialog box that can be used. We'll cover this in greater detail, but one of the things you can do here is you can change the size of the screen. This left pane here in the main window, you can adjust how big it is by changing this parameter. So if I change it to 0.8 and hit apply, it'll shift that over a little bit, so you can give yourself a little more room on the screen if you feel like you need it. I'll change this back to 1 and I'll leave it there. The nonlinear modeler actually has two topologies you can choose from. That's done in the options dialog box again. So if I click on large, it will show a larger model with some more elements in it. And the smaller model, we'll talk about this, about what these different models are meant to capture well, right now. So this slide generally shows what these two different topologies are meant to capture. This is a speaker application where the sound is radiating from a port. This is largely meant to capture the behavior of high audio speakerphones on cell phones and tablets and whatnot. These generally are put in the devices in a box form these days. That box will have a speaker in it. It'll have a rear volume and then a port leading out to the outside world. And generally there's a screen in there to keep foreign material out and to apply some and to apply some damping, not nonlinear damping, but damping, acoustic damping. This topology here is meant to mirror that. Here the speaker is meant to represent this speaker. This rear volume is the small rear volume in back. The port leads out here to the material. Then here's the material. And the radiating port actually does allow you to enter a port length inside. So this little port extension here is specified in the radiation element. The large model is very similar, except it adds a lot more detail. On the rear path now, you not only have a rear volume shown here, you also have the possibility of a material behind the speaker, which would be R3. You can have an internal volume captured by this port here, and then if there's another acoustic port leading to the outside world that would be captured by these last two elements. If you only have a rear volume, you can go to the modeler and just specify infinite impedance for this element that's captured with the wall for the impedance of that. Show you that real quick here. So we'll bring up the large model, and if I click on this element, you specify what material you want to use with this drop-down box, and you can just specify wall, and that will basically provide an extremely large impedance for that element and kind of cut off this this acoustic path. I'll leave it as no mesh for now. I'm going to go back to the small model since most of my work is going to be done on that. To solve for the model, you hit the calc button, very similar to the linear modeler. The results are shown in these graphs. Presently, we're graphing the radiated sound pressure level that's radiated out of this port, the THD that's predicted at the listening point. So the listening point would be 100 millimeters away from the exit port, and then the velocity through the material is also being plotted. The nonlinearity of the material is going to be dependent upon its velocity, so it's worthwhile to plot that quantity. Presently, there really isn't any nonlinear elements in here, so the THD is quite small. The nonlinear components that are modeled with this modeler are the speaker and the materials. The speaker's nonlinear behavior is captured in a BL curve and in a compliance curve. This nonlinearity is specified by providing a power expansion series for the BL as a function of the speaker displacement. This is shown in the manual. The nonlinearity of the material is specified through some nonlinear parameters which are captured in a material database. So let me show you this, how the nonlinear BL data is entered in real quick. To do that, I'm going to take us to the manual, which can be brought up by going to Ares, selecting help, and bringing up the nonlinear modeler module. Here's the manual. If I go down to the point where we're talking about the speaker and its parameters, here it shows that the BL that's used in the model is actually a function of displacement. And you can enter these power coefficients by just putting spaces between the different coefficients in the parameter box. The first coefficient is just a static coefficient. The second one is linearly proportional to the displacement x. The third one is x squared. So I'm only going to concern myself with symmetric distortion at this point. So I'm going to enter some fictitious BL coefficients where the second coefficient here, the one that's dependent upon x, is going to be 0, but the x squared one is going to be negative and large. It's large because x is in units of meters, and this is the displacement's quite small. It's in the micron range, so we need a very large coefficient there. So I'm going to enter this into the modeler. Go to speaker, and make the first coefficient just 1, second one 0, and then -1 e to the 6th for the displacement squared part. I'm going to go ahead and hit, actually before I get going, I'm going to change the length to 10. I want to show this for a 10 millimeter long port. I'm going to go ahead and hit calculate, and the results are shown here. I'm going to go to the graph element. I'm going to make these lines a little thicker so they're easier to see, and I'm going to copy this result into buffer A, and I'm going to label this speaker displacement or speaker distortion only. So by entering the right coefficients, you'll capture the nonlinear BL behavior of the speaker. Same can be done with the compliance, but I'm going to leave that as linear for now. The nonlinear Material behavior is selected with that list box again. When you receive the Ares installation files, you get a series of files, and this one here contains the nonlinear material data. So if you need more recent material data, all you have to do is update this file from SATI. But if we return to the modeler and we click on the material element now, I'm going to go ahead and select acoustics 6 for 6 rails, and I'm going to run the simulator with that material. And we have quite a bit of distortion that's showing up from the material. So the green curve is the distortion just from the speaker, and the blue curve, which is hiding behind the green curve here, is the distortion from the speaker and the material. So you can tell with a poor choice of material, you can end up with quite a bit of distortion coming from it. So if you're using Ares to help you with your nonlinearities that you're seeing in your design, if you're trying to reduce THD, you really need to understand the main mechanism that's generating this distortion. And I'm going to take you through a couple slides that talks about that a little bit. So on this slide, we see the graphs generated from the modeler. This is showing the SPL response from the speaker in blue, and if we add the mesh, we have its response, a 6-rail mesh, we have the response in green. The major effect on the SPL curve with the mesh is that it adds a little bit of damping on these resonances. You can also plot the velocity of the air, particle velocity of the air, through the material. That's shown in this graph. Again, the major effects of the material is to lower the velocity at those resonant peaks. And then finally, you can see the displacement of the speaker as a function of frequency. And again, the material is lowering its displacement a little bit. Now, we know that the nonlinear behavior of the speaker and the material is based on the displacement of the cone and the velocity through the material, respectively. So looking at these curves, we might expect to see most of the distortion occurring at 1 kilohertz and about 2.5 kilohertz. However, on this next slide, I'm going to bring up the THD curve as well. So these slides are kind of running together here. I apologize for that. But this is the THD curve for that model. The blue is the THD without any material. That's just the distortion from the speaker. And in this particular model, the green curve is the THD with the material in place. So you can tell we are getting some distortion at these velocity and displacement peaks, but most of the distortion is not at those frequencies. We have a big peak due to the speaker down at a little over 300 hertz, another peak due to the speaker at 800 hertz, and then the material makes it worse from about 800 to 1,000 hertz or so. So this doesn't correspond well to what we're seeing with these displacement and velocity peaks. To understand why that's the case, we need to go to the equation for THD, or total harmonic distortion. It is a function of not only the harmonic, what's happening at our base frequency, but it's a strong function of what's happening at the harmonics, the power in the second harmonic, third harmonic, and so forth. Another thing I want to point out is that if we have symmetric distortion, which is the case that we're currently looking at, the BL distortion that we've entered is symmetric about the zero displacement, and the nonlinearity of the material is symmetric about zero velocity. So if you're looking at a symmetric distortion, turns out you're going to generate odd order harmonics primarily. So to understand what's happening to distortion down here, we have to concern ourselves with what's going on at the second, third, fourth, fifth, etc. order harmonic. So it's going to turn out that we have a THD peak down here, not because of what's happening here so much, as opposed to what's happening at the higher frequency. So if I go to this graph, we have a THD peak a little over 300 hertz, about 330 hertz, and it turns out the third order harmonic occurs at this peak in the pressure response. This peak in the pressure response means that the system is able to radiate that frequency better than other frequencies around it. As a matter of fact, it can radiate 1000 hertz 35 dB better than it can radiate 350 hertz or 330 hertz. So even if the harmonic generated by what's going on at 330 hertz is 35 dB below the fundamental, they radiate about equally when you take into account the radiation efficiency of the system with that third harmonic radiating at 1 kilohertz. So the cause of the impedance peak, cause of the THD peak at 330 hertz isn't really a factor of what's going on at these lower frequencies with the velocity, but it's a matter of what's going on at these at its harmonics, the third and even the seventh order harmonic. It is interacting with this peak here, and the same is the case for this peak at 800 hertz. Its third order harmonic is corresponding to this peak, so that's why we have a peak in the response in the THD here, peak in the THD here. Things are a little blurred out when you take the material distortion into account. We are having a strong effect due to this velocity with the material, but that's accentuated by the fact that we've got a peak in the response with its third order harmonic up at around 2.5 kilohertz. So I wanted to show this to you and point this out to you so you have a better understanding of what's going on with this THD generation. I'm going to go back to the modeler and run a little example here. So we've already shown the THD effects of the material in the speaker here. I'm going to now iterate on the length of this port, and we can see some geometric effects. So I'm going to press the iteration button. This will run a few times. And now we see a series of curves showing the effects of the length of that port. When the port length is, I'm going to turn that speaker only one off. So the port length is long with purple and short with blue. So here's the THD. When the port length is long, we have a lot of THD at 1 kilohertz. When the port length is short, we have very little THD. So this is showing some of the geometric effects of the model on the THD that's being generated. The reason for this is a little complicated in terms of the physics, so unfortunately I'm not going to go into it here, but it has to do with the voltage on that speaker being a pure sine wave. There's no distortion in the voltage, and as the speaker is more closely acoustically coupled to the material, you force more of a linear velocity, an undistorted velocity through the material. So making that port length short is one of the things you want to do to improve your nonlinear design. So I mentioned previously that there are a number of solvers that you can use. One difference between them is how this port is handled. In the linear solver, this is automatically handled as a one-dimensional waveguide, but to take the waveguide features into account with the nonlinear modeler, you have to discretize this up quite a bit so that runs, so the solver runs quite a bit slower. To speed that up, I've got the option to select between a solver that treats it as an extended reaction, which isn't shown in the name here, or as a lumped parameter. So if we select the lumped as we've been doing and hit calculate, this runs fairly quickly. If I now go back and select the typical solver and I hit calculate, it runs quite a bit slower, particularly as we get to the higher frequencies, as the discretization of that port has to be increased more and more. So there is a little bit of a difference between the two solvers. If I copy this in the buffer C, go back, reselect the lump parameter solver and hit calculate. You can tell that there is quite a bit of, there is some difference between the two. And it gets greater as you go to higher frequencies. But the non-lumped solver is quite a bit slower. So what I generally do is I will do some initial design work with the lumped solver, and then when I go to fine-tune the design, I'll switch to the solver that treats that as one-dimensional waveguide and fine-tune the results from there. So I don't spend too much time burning CPU on the solver. There's also a frequency domain solver. So I select that and hit calculate. You don't get any distortion results from it, but you will get frequency response results. The frequency domain solver is just mostly useful to get quick ideas about what size of volumes and ports you want to have to optimize your frequency response. However, chances are you've done the linear part of your modeling in the linear modeler in Ares, so that might not be quite as useful. I'm going to switch back to the lumped time domain, nonlinear time domain solver. I mentioned that the time domain solver has to discretize this port when you have an extended reaction. How much discretization you have depends upon this parameter here, number of wavelengths. That should be read as number of discretizations per wavelength in terms of the port. So if the wavelength is very long, you don't need many discretizations in the port. But as the wavelength gets short and you get multiple wavelengths in that port, you're going to end up with a lot of discretizations. In this case, the default is 100 discretizations per wavelength, which seems to work pretty well. But one alternative is to use the non-lumped solver and go back here and so if I hit calculate now with 100 discretizations, this slows down quite a bit as we get to the higher frequencies. I'll hit stop. If I reduce this by a factor of 10, we still get some discretizations, but it goes through the frequencies quite a bit faster. So you can adjust this parameter. And each port length has its own number of discretizations that you can enter. So if we go to the large model, hit OK. Each port that you find here has its own number of discretizations per wavelength that you can enter. Okay, so I'm going to go back to the small model. I'm going to go to the options dialog box. So I mentioned how you can select the model and change the layout a little bit. There's a limited ability to import SPL curves into the graphs here. To do that, you just have 2 columns of data in the clipboard and select this paste button. So if we want to paste some data into, let's say, buffer F here, I've got another Ares window open elsewhere on my computer. I'm going to copy this data to the clipboard. So if I right-click and select copy the current trace in, if I now launch a Notepad program, I can paste that in, and I can see that what that did was it entered 2 columns of data. This is frequency. This turns out to be SPL. I know that's in the clipboard now, so I can go back to my nonlinear model here, and I can hit paste into buffer F, hit OK. If I now go and plot buffer F, I've got that data in my SPL curve, in case you're interested in that. Another part of the options menu, options dialog box, is the ability to process audio files through the nonlinear solver. So if you want to hear the effects of this distortion on some audio file, you can use this wave processing block here. I'm just going to do a quick demo here of a sine wave. Now I know I have a distortion peak at about 330 Hertz. So I've used Adobe Audition here to create a 330 Hertz sine wave. that I'm going to process with Ares Nonlinear Modeler. To do that, I first need to select the input file, and I've got the 330 Hertz full scale wave file here. You then need to specify what a conversion from the wave file levels to actual voltage, and that's done with this parameter here. How many RMS volts does a full-scale sine wave represent? And right by default it's 2.5 volts. I'm going to crank this up to, I guess we've been doing our analysis at 3 volts, so I'll set it to 3. I also need to specify an output file. So as an output file, I'm just going to use the same file name and just type out. Then to convert the output SPL back to a wave file, I need to know, what full-scale wave file would be in terms of SPL. I believe I need to make this a little bit smaller, so I'm going to make this 95 dB, and I'm going to hit process wave file. As it runs, there's this little counter on the main screen telling you what percentage of the wave file it's processed. So it's done. If I go back to Adobe Audition now and open that processed wave file, it's a little low, but if I zoom in, hopefully we're going to see some distortion effects. And you can tell that that is indeed a slightly distorted sine wave now. So that's an example of how you can process an audio file. You can process speech files as well as pure tones and listen to the difference. I find it very hard to hear much of an effect on audio files. I think you really have to be a trained ear to pick that up and pick up the nuances between 2%, 5% THD distortion, but it is possible. Okay, so this is all I'm going to cover in this video.